So as I noted before, the numerical integration techniques comes in two forms. Either we have explicit data tables, or we have some type of function that we need to integrate. Now, data is limited to by the number of points, whereas with a function, we can generate many points and try and capitalize on developing an efficient integration scheme. But that means we have to have the function. So we're going to explore Romberg integration and Gaussian quadrature. And first, if we look at Romberg integration, and as I mentioned before, we're going to capitalize on the ability to generate many function values to develop our efficient integration scheme. So the Romberg integration is a recursive method that combines a successive integration estimates to generate a third, more accurate estimate of using some weighted combination of our integration. That is, I can be approximated or improved upon by some weighting factor 1 multiplied by I1 plus our weighting factor 2 multiplied by I2, where the sum of the weights is equal to 1 and weight 2, let's just undo that, weight 2 is always greater than weight 1. And it's based on a successive application of the trapezoidal rule. And in general, the algorithm is written as the improvement in our integration, ijk, is equal to 4 to the power of k minus 1 multiplied by I, j plus 1, k minus 1, minus I of j, k minus 1, all divided by 4 to the power of k minus 1 minus 1, where k is the accuracy order of the integration. So, for example, k equals 1, we're talking about a first order accuracy integration. And so, for example, if k equals 2 and j equals 1, we have I of 1, 2 equals 4 multiplied by the integration of 2, 1 minus I of 1, 1 divided by 3. Okay, so what this means is that our updated integral, so we're updating going from k1 to k2, hence our updated integral has 2 in it as an underscore subscript, and we rely on the previous two estimates of our integration, 2, 1 and 1, 1. So we rely on the first order accuracies to generate the second order accuracies. In this instance, W1 is equal to negative 1 over 3, and W2 is equal to 4 over 3. Alright, so it might be a little confusing, so let's just look at this, what I mean in a tabular form. So remember, it's based on the trapezoidal rule, which means we can just set up the following table. And I'm going to say m being our intervals is 1, 2, and I'm going to double it at each time, 4, and 8. And here on the columns I'm going to put the order of accuracy, so order h squared for k equals 1, first order h to the 4 for k equals 2, and let's go to order h to the 6th, k equals 3. Remember, these order terms are referring to the error that we will generate. So the higher the order, the smaller the error. Okay, so at m equals 1 and k equals 1, we have the integration I1, 1. At m for 2 segments, at our first order integration, we have I2, 1. This will be more accurate than 1, 1. So therefore, in order to get our improved accuracy at I1, 2, I'm going to need to use minus 1/3 weight of I11 and a 4/3 weight for I21. Okay, and we carry on. So if we have 4 intervals, we have I3, 1, and 8 intervals will be I4, 1. Alright, now in order for me to get an improved accuracy for the second order of accuracy, I need I21, take minus 1/3, and I31. Okay, now that I have these 2 points, I can calculate another more accurate integral that is using weights minus 1/15 and 16/15. And that will give me I1, 3. So you can see how the weights are used to generate or to improve our estimates of the integral.